right, so first, can you all hear me? Is this loud enough? Yeah? All right. So first, thanks so much for the invitation. It's my first time in Pittsburgh and it's been great. And thanks for the chance to get to talk. So what I want to do today is to tell you about some forthcoming, hopefully very soon, like within the next 2 weeks, paper with two people in the audience. She, who is sitting somewhere over there, and Maria, who will speak right after. Any mistakes I make are mine. Everything in the paper will be correct, thanks to them. Okay, so I realize the title is probably very mysterious, but hopefully it will be less so. So the standard answer to what is a theta angle is as follows. Okay, so theta angles are just periodic parameters that you get whenever there's a topological term that you could add to the action that's built out of the fields in a particular quantum. And we all know many, many examples. So for this audience, maybe the most famous one would be the Yang-Mills theta term, which I wrote right here. It's very important. People have spent decades thinking about these things. So what do theta terms do at a conceptual level? Again, I think everybody here knows, but it's nice to review. Basically, whenever you have such a term, the space of field configurations in the path integral splits into different topological vectors. That's what this is intended to indicate for the percussion function. And then turning on a theta angle basically changes the relative weights of the different topologicals. Okay, so that's all a very familiar story. Oh, I forgot to say, please don't hesitate to interrupt me at any point. I suspect that nothing here is controversial, but other things I say will be, so just ask questions, okay? So what I want to do, okay, is I want to, for the purposes of this talk, I want to call the kind of theta angles that I just described, which are the ones I grew up learning about, as Lagrangian theta angles. What I mean by that language is to write them down, you need a Lagrangian, or at least an action. Because you need fields in capacity. Okay. Now, Lagrangian theta angles are of course very interesting, but I think it's worth noticing that they are not intrinsic parameters for quantum field, because they depend in detail on the fields that you use for your path integral. And for example, one quantum field theory could easily have multiple Lagrangian descriptions. Okay, so that came up in Phillips talk, for example, on Wednesday. And a theta angle in one of its weakly coupled descriptions does not remotely have to map to a theta angle in some other weakly coupled. Basically, they depend on the description. So they're not generally intrinsic parameters of the field. To be clear, I'm not saying that makes them uninteresting. They are fascinating, but that is an interesting thing. Yeah.
And so, even if you have different descriptions, changing theta changes the theory. So why don't?
Yeah, well, so a theta angle in one theory might conceivably map to some other kind of.
Might give it a different name. So
it's a parameter, but it's not necessarily the same type of. I mean, there's not necessarily an there's no statement that the topology of field space is preserved across the topology.
why talk about that way? There's a family of theories.
Yeah.
And call it whatever you want. Some level or other, it's going to be equivalent to the.
Sure. Well, the reason I'm talking about this is I'm about to introduce theta terms, theta angles, for which none of this can be said, and they're defined purely intrinsically.
But I assume that it's kind of even with Lagrangian, it's kind of the way you describe it, it could be different. But original definition of theta angle was associated with, say, you're applying some shifted wave function, and you're saying that the multiplied by phase, say, path following a circle, or and it is the definition of theta. Then you can discuss how to describe it in Lagrangian, but not in.
Okay,
so
I think that I see what you're saying, but I still think that there's not. You see, to talk about theta angles at all, you first need fields. And when you start talking about a wave function, already that notion basically says you have a path integral in your head secretly.
Oh,
That's right.
it's all a wave function.
It's
the same.
Characterizing it. We also sometimes talk about field theories in CFTs in terms of CFT data.
Yeah.
We don't need to talk about it Lagrangian, but we still have an N equals force for analysis of the family of CFTs. If I tell you what the CFT data is, the data is one of the ways that you
Can you define the theta angle?
Yeah, you look at any particular CFT data which is sensitive to theta, and then that you have a family of values for that OP coefficient as a function of theta.
And it is quantum mechanics, it's not a, look, it's not, quantum mechanics, it's not, of course, you're very factually there, but there is a simple operation which is shift. And you are saying that we are applying, so it's a symmetry of the theory, if you like. You're applying the
Theta angles.
Why not?
No. Okay, well,
so-
I don't think so. I disagree. So, yes.
But okay, then
saying that they angles are wrong.
It's the parameters, yes. Just like a gauge coupling is a parameter, but it's not a, yeah.
It's not a way of saying this is a gauge coupling, this is a theta.
Precisely. Precisely,
Okay.
precisely. It's a parameter, just like the gauge coupling, but it's not. Yeah.
so the particle,
That's
the
right.
particle, just a moment, because the particle in circles, there is no theta in Lagrangian, but theta still exists.
Of course
So-
it exists.
Yeah, right, but so, and exists in the sense I'm time.
What symmetry does it relate to? Okay.
By too far?
That's a gauge redundancy. Let's talk about it another time. Let's talk about it another time. This will take us a long time, but that's a gauge. That's not a
discussion to a panel.
Let's. That's right. So we will have a very entertaining panel. Okay, so, the question that I wanna try to ask and answer in this talk is, are there theta angles out there that are simply not at all what I, like what I've just described? They're not Lagrangian theta angles at all. Okay, so, you might wonder what the hell this would even mean, but let me try to convince you that they exist. So I'm gonna start with a punchline. Okay, so my claim, or our claim, is that there's a big family of like a different type of theta angles entirely, which we're calling symmetry theta angles, that have some overlap with Lagrangian theta angles. I'll tell you about that. But in general, they're quite different. And before you get worried, they appear in pretty familiar field theories. So that makes them quite interesting. They have effects. Okay. So I'll tell you how they're defined momentarily, basically going on the next slide. But first, let me just mention a few of their properties that what your appetite. So these symmetry theta angles are, you can associate them to with like non-anomalous global symmetries of the theory. Okay. If you have a non-anomalous global symmetry, it doesn't necessarily mean that there exists a non-trivial symmetry theta angle, but it could exist. And whether it does or not depends on the global. But their definition is purely in terms of the symmetry data of the theory, and hence they are completely intrinsic parameters of the field. Like I said before, but you'll see they appear in quite familiar field theories, and they have interesting applications. And they can be discrete or they could be continuous, but when they're discrete, they are RG invariants. And that means they can be used to label universality classes of field on the same footing as Tilton numbers. So we have worked out the classification and properties of these types of theta angles, assuming that we're dealing with symmetries that are abelian group-like symmetries. Okay? That already gives a large class of interesting theta parameters with interesting applications. And we suspect that there's an extension to more general symmetries as well, but like non-abelian symmetries, for example. But that involves major technical implications, and so we have not really tried to push that so far. This already kept us quite good. Okay, so how do you define this? Okay, so the definition is going to sound quite abstract, although it depends on your backgrounds. For some of you, it may be completely trivial. For others, it may sound very abstract. Rest assured, I will ground it in something extremely concrete shortly. But first, I want to just say the definition and then define the terms that go into it, and then give you an example. Okay, so let's take a quantum field theory. I'm going to give it a name Z. Okay, so secretly, I'm also going to be thinking about a partition function, which I'll also call Z. And let's suppose that this quantum field theory has a non-anomalous abelian group-like symmetry, G. Okay? And then the idea is you take this theory and you hit it with some kind of transformation, topological manipulation, actually, which produces a new field theory, which we claim can be interpreted as the original theory with a new theta angle turned on, defined by this procedure. So we're calling that transformation capital theta, and it is a composite of some well-known topological transformations of field theories from the literature. So they are called conventionally S and S dagger and T transformations. So if you've never seen them before, this is completely mysterious. If you have, you might already know what I'm going to say for the rest of the talk. But let me just say, what are these transformations? Okay, so this so-called S operation, you take your global symmetry G, and you find a way to gauge it in such a way that you get a new field theory where you haven't introduced any new degrees of freedom, and you get a dual global symmetry in some way, okay, which I'm going to call G hat. The S dagger operation is then gauging G hat, again, without introducing any new degrees of freedom. In such a way that you get a dual symmetry again, but the dual symmetry is just the original symmetry G, one second. And you can show that if you do first one of them and then the other, it's like doing that. Okay? Yes, there's a question. Not necessarily. So hold that thought. G is not necessarily finite. It could be, that's an interesting possible example. But G could be U1, in which case you have to ask exactly what's the speed, how you do it. I'm not sure. But it's a billion. It's a billion. I don't know if it's not a billion, that's hard. Okay, so yeah. I mean, when it's finite, it's also a billion. It's always a billion. This talk is always a billion. If going to another billion immediately brings very interesting tell you. And I'm happy to tell you how. And then there's an operation which is often called T in the literature. So that is so you start here, you do this S operation, you get a model with a new symmetry G hat, okay? And you stack it with an invertible field theory, which is G hat symmetric. Okay, that just means multiply its partition function by the partition function of some so-called invertible topological theory. And at that step, these theories are parameterized by some periodic label theta, which could also be discrete or it might be continuous. This depends on it. Good. So the theta transformation, which I claim gives you these right classes theta angles, is a composite of these, where you first do this, then you do that, then you do that. Okay. So this is very abstract. So I want to give you an example. Okay. So here it is. Let's take a four-dimensional quantum theory. Once in my life, I'm actually talking about 4D. With a Q1 one-form symmetry, which is associated with some two-form background field. Okay. And let's say it has a partition function. I haven't told you which precise theory this is. If you want to think of it as Maxwell, feel free, but you don't have to. And now I want to define an S transformation. I want to make it concrete. And here, this is the continuous case. Okay. So the way that we can do it is we can borrow ideas from old papers by Kapustin and Strassler and Edwin from like 20 years ago. And we simply gauge, make this background gauge field dynamical, renaming it to lowercase b in the process, and don't add a kinetic term, but instead write this BF coupling. And the BF coupling is a coupling to a classical background field C, which if you check the form degrees here, it's a 4D theory, C has got to be a one-form gauge field. And it's actually a background gauge field for a dual symmetry, which is a U1, U1 0. So that's what she happened. Okay, so you may wonder what the point of that is. Well, if you now do an S dagger transformation, meaning you gauge the new symmetry, okay, just do it. Okay, and again, you add a BF term with some new B, which has to be a two-form now for consistency. If you carry out the integrals, some identities involving BF theories will tell you that you get a delta function, which sets this B to B prime. And so you get back to something which is the original theory with some background field for its one model. Okay, any questions? All right. Okay, so that's the S and S dagger transformations for that example. Now, what about this invertible symmetry? So what's an invertible symmetry? Sorry, what's an invertible theory? Anyway, an invertible theory is just something that has a pure phase partition function of any manifold. They're almost trivial. In our case, they have to be built out of the background gauge fields for the G hat symmetry. That's what I mean by G hat symmetric. That would be gauge invariant, background gauge invariant. And also, we require them to depend only on the deformation classes, topological deformation classes of these background gauge fields. And that picks out a unique possible invertible theory, which is characterized by a 2 pi periodic theta angle, which looks like this. Okay, so the T operation is replacing this dual field theory with the same thing, with multiplied by squeeze. And then to get what we allegedly want, I claim that we want, we need to, having done this, we need to carry out the path integral over this gauge field. And then we should get back to something which you can interpret as the original theory with some kind of theta angle turned on. And so that's what this would look like. And at this point, you might be wondering, like, can I make this more concrete? And the answer is yes, because if you say that the theory that we've been working with has been Maxwell theory this whole time, then the reason I'm going to do that is that it has 2 one-form symmetries, a U1 electric one-form symmetry, which counts Wilson lines, and U1 magnetic one-form symmetry that counts as both bonds. So good. So we have a U1 one-form symmetry, at least one of them. Actually, we even have 2. So let's start with Maxwell theory without any conventional theta term, and then we can apply this transformation to the magnetic symmetry. Okay, and the way the magnetic gauge field, background gauge field couples to the dynamical photon gauge field is like that. And you take this idea, plug it in here, do a bunch of algebra, and what you'll find is that the new theory after hitting with this transformation is literally Maxwell theory with a theta, the standard thing. So the good news is that this operation, which might have sounded utterly bizarre when I first mentioned it, that I claimed should give theta terms, indeed gives a theta term in this one specific example, which we easily recognize. The possible bad news is you might be thinking like, well, that's really cheap, because the way that I constructed this, we just wrote a standard theta term in the Z hat theory, right? I mean that's a theta term. So like, am I just like just renaming standard things? But I'm not so sure about that, because I think there's a huge conceptual difference from the standard method of defining the Maxwell theta term. So here we defined it purely from the symmetry data associated with the U1 magnetic. The normal way of doing it is just to write a term in the Lagrangian and leave it at that. Okay. The Lagrangian in this approach only appeared when we started trying to check if this particular symmetry theta angle might look familiar if we commit to a familiar Lagrangian, and it does. But the method of constructing it is genuinely different from the standard way of thinking.
But in this case, just that is not reflected.
Huh?
There is no physics dependent on.
Wait until Maria's talk. That's a common view, but it is not correct. Yes.
So we've done the same thing, but we don't know what.
Thank you. That's my next slide. Okay. Now you might wonder, is there a second theta angle in Maxwell theory? It's like I planted you in the audience. Okay. Now, in U1 Maxwell gauge theory, there's U1 electric, right? You could have applied the theta transformation to that instead. Now, you would get a symmetry theta angle from that, okay? And it would have a simple Lagrangian description in the magnetic dual variables, but it would be very confusing looking in the original variables. But anyway, you might ask, okay, so does this mean there are 2 theta angles in Maxwell theory? And the answer is no. And the reason the answer is no is these 2 symmetries have a mixed anomaly. You cannot apply a transformation to both of them at the same time. That would be inconsistent, because we need to do gauging and you can't. Okay. And in fact, these 2 would be distinct theta angles in Maxwell. They're actually just images of each other on their EM duality, so they're secretly one theta product. That was the S duality in Phillips talk. Yes. This whole, yes, I would call that a generalized theta angle. I think it's a consistent. So it's not the way people normally. So there are cases where you apply this technology, and the thing that we're calling a theta angle, other people might have called something else. But I think this is a consistent general language that actually is quite a good way. But yes, yes.
How general is this perspective that that's normally is really telling you that that's the same thing on the S duality?
That's a great question. I'm not sure how general it is. Let's talk later. I'm not certain. Okay. I have a suspicion that there's something to it, but I'm not sure what general. So what we just found, okay, is that the Maxwell theta angle lives in this intersection. Okay, so it's both a symmetry theta angle, but it's also a Lagrangian theta angle in the electric duality frame of Maxwell theory. And that's because the U1 magnetic symmetry is a solitonic symmetry. In that duality frame, it only acts on a 't Hooft lines. And you can show, or we have shown in our paper that will come out soon, that that's always going to be true if you have solitonic symmetries. They're going to sit somewhere. Okay, but not all symmetries are solitonic. In fact, that's kind of rare. So, good. So the next thing I want to mention, okay, Yang-Mills theta angle. It lives there. It's not a symmetry theta angle.
But still, I have to return to quantum mechanics. You have a look at a circle, and you're saying that 2 pi is equivalent to 0, right?
Yes.
And what I'm claiming is that in any field theory, it's actually the same. Because you can find
Okay.
this power unification
Yes.
and then put associated instead.
Yes, I have no complaint about that theta angle, but it's a little bit orthogonal to what I want to say. So can we discuss that later?
Yeah.
Good. So the reason I want to say that the Yang-Mills theta angle is not a symmetry theta angle is that it's a continuous thing. So if it were a symmetry, to be a symmetry theta angle, it'd have to be associated with a continuous global symmetry. That's how it works in our formalism. But there's no continuous internal symmetry in Yang-Mills. Unless you allow maybe the notion of -1 from symmetry, but that's very circular. So yeah. Now, the thing that may be more interesting is, what lives out here. Okay, so good. So let me give you some example. If you take U1 gauge theory and add electric matter with charge Q and magnetic matter with charge M, you'd get something called a Cardi-Rabinowitchi type model. And the one-form symmetries would get reduced from U1 times U1 to like this size. Okay, from discrete symmetry. And now, if the greatest common divisor of Q and M is 1, so they're co-prime, okay? So like 2 and 3 works. There's a very nice paper by Clay, who may be somewhere in the audience, with Kantaro Omori, that showed that the mixed-up phenomenon actually trivializes in this case. It vanishes. There's no mixed-up phenomenon. And therefore, there's no obstruction to a strongly coupled trivially gapped phase. It'll be strongly coupled, but it should exist. And in such a phase, the one-form symmetries cannot possibly enhance the U1 symmetries in the IR. That's something that I showed with Theo Jacobson a couple of years ago. So anyway, so you can apply our construction to both of these at the same time. Nothing stops us. And then you get 2 independent theta angles that are discrete. So what does that do? Well, it induces some interesting interference phases for strings. So Maria will say a little bit about that. Let me move on. Okay, so these theta angles live here. So what I want to do is I want to skip a bunch of slides, and I want to finish with a comment about the standard model because I'm running out of time. So my last example, okay, is if you open a standard textbook on the set on UOT, they'll tell you that the gauge group of the standard model is that. Okay. Now we don't actually know if this is right. There might be a discrete quotient here by Z2, Z3, or Z6. And that's been much discussed recently. Like what signatures does that have? Observationally, in papers by David Tong, Clay Cordova, and Portion Sin and Raul Gomez and others. That's all very nice, okay? But suppose that the standard model gauge group really is this textbook naive. Okay? In that case, there is actually a Z6 electric symmetry in the standard model. That's because even though the standard model contains fundamentals of SU3, for example, as we call it, works, there's a combination of centers of these 3 different gauge groups that acts trivially, and hence there's a one. So, well, if there's a one-form symmetry, and it's a 4D theory, I can take the machine that we have, hit the theory with that machine, and produce a discrete theta, okay, which I'm going to call theta E. It will take values which are either 0 or 2 pi over 6 or 4 pi over 6 or whatever. And we claim that this is an extra and currently unmeasured parameter of the standard model. At least it could be if that's the gauge group. So what does this parameter do, and how do we know it's not measured? Well, what we can show is that it doesn't affect any local observables in the standard model. That's why it's not measured. But to see what it actually does, we have to use the fact that the standard model also has a U1 one-form magnetic global symmetry. Thank you. Perfect. Which comes from the hypercharge. And there's a mixed until anomaly between these 2 one-form symmetries, and that means that when you turn on this theta angle, you get a kind of generalized Witten. And so how does it go? Well, imagine you have a line operated with charge under the Z6 electric symmetry. You turn on this funny new theta angle, and this Wilson line will pick up a U1Y magnetic charge, theta E over 2 pi times n. This is like the dual or the opposite of the usual Whitman effect, where electric charge becomes fractional. Here, the magnetic charge becomes. So, what's the pheno punchline? Well, I'm not a pheno person. This isn't some early, this is like the subject of early discussions with somebody who actually knows pheno, but please don't blame him if what I'm saying is wrong, because it's very early. But if we couple the standard model to a BSM particle that breaks the Z6 to nothing, so for example, it could be this representation. So trivial under color and SE2 left, but charge 1 under hypercharge. Okay, just imagine you do this. Then you turn on this funny theta angle, and it will give this funny BSM particle a fractional U1 magnetic charge. Yes.
This is six or concept break or
And
after integration is goes on. That was
it's spontaneously broken. But it's not, it's exact.
But because this whole paper by Anselmo and Garganson who brought this theta angle, I mean, it would be theta angle very heavy, right?
This is different.
It's the same.
This is different. It's orthogonal. It's orthogonal to that. Yeah. This is not the electric thing. So the punchline that I want to get to, and then I'll shut up, is that here you can get a fractional charge magnetic monopole whose mass has no connection with the gut state. That's interesting. That's pretty interesting. Okay, so I'm out of time. So I just want to say there are many open questions. If any of you have ideas about them, please talk about them. Thank you for listening. Can you say it louder? I couldn't hear you.
I'm serious. It's part of the joke, but people are not involved. They say that it was wrong. I want to act about the same. It's sort of not new.
Not new. Very good. Thank you very much. Okay, so there's a sequence usually, right? Yes.
Could you explain what is conceptually different in your thought in comparison to what is, say, discussed in the standard data with Haroni, which you know in Blackbird? They explain that you have, let's say, SQM theory and again.
Yeah, I know what you're saying. Yeah, it's conceptually different. It's on a mechanical level, it's very similar, but it's conceptually different.
So let me add a question to the following. Consider the one actual theory. Now there are fundamentally many ways to that's the end. Therefore, you can easily show that all possible maximum theory, meaning that all possible values of theta are orbital function. So and therefore you can reproduce theta angle like you did in the top by orbital with any particular factor.
Well, that's nice.
But I think that's what you can.
That's
So what is conceptually?
so for example, in the paper, I don't know, I mean, you said several different things in the, I don't want to try to address all of them live, but for example, the comparison to the paper by Haroni, Cyberg, and Tachikawa is that their interpretation of these kinds of STS transformations that we're talking about was that they take you from a gauge theory with gauge group SUN, and they wanted to say that they would take you to some gauge theory with a different gauge group. So they weren't thinking of these things as the same theory. And that's a consistent interpretation, but I think it's not the most useful one. And not only that, they really focus on the 4D example. We have a completely general story that is not just about standard 4D gauge theories. It's not just about 4D, et cetera, et cetera. So it's a conceptual change.
Well, this paper was written more than 10 years ago.
Yes.
Since then, people
Yes.
introduced this plus one-dimensional topological theories, which really solve
Yes.
all this stuff.
So if you can send me a reference that did all this, I'd be very happy to read it. Let me leave it at that. I don't think it's what you're saying is correct.
In 2 dimensions, it's a lot like JJ bar deformation.
Sorry?
In 2 dimensions, it's a lot like JJ bar deformation.
It's similar. It's very similar. It's very similar. So for example, this Cheshire theta term that you might have heard me talking about last year at the New York, it's very closely related to that. And it's also an example of a symmetry theta angle. So in the 2D case, yes, I think there's a relation to J bar. So I should say, it's not like, sorry, just to return to Anatoli's point, I mean, it's not that we're saying, what we're saying is like disconnected from the literature and it's some, it's, of course it's connected, but I think it's a new perspective.
You're saying that there is either within a civil that you can protocol it and obtain in the field, right? But that's not entirely what we thought. And you're saying that in your theory, sometimes can be related by an old theory by
Yes.
something else.
Yes, yes.
That is also not entirely.
Okay.
So I'm trying to understand what is the question of the community.
Okay, I do not think that people have thought about these kinds of transformations as generating theory from the ground. Okay, I don't think that's been a perspective, and I think it's that the perspective is valuable because it allows us to say things that certainly have not been said before about applications of this, about its implications, some of which you'll hear about shortly in Maria's talk. Yeah, so it's of course connected to things that people have done, but I think it's new.
So, yeah, so that, like, is it obvious or is it?
Hamiltonian. I have okay, the quick answer is I haven't thought about it. In principle, the whole procedure is independent of representation of the theory that you choose to use. So you just do the same thing, because I didn't commit to Lagrange yet, right? That's the whole point. I don't have to commit to it. So naively, the first answer, even though I haven't really thought about any concrete things about the Hamiltonian, is naively just do the same thing. But
Monetization of theory implies that you know how to construct a Lagrange, and it's a
yes,
tool to construct a Hamiltonian, not more.
well,
Because tonight.
there are theories that have no Lagrangian, but do have a.
Tonight, the conceivable, you need to know Hamiltonian, not more. Lagrangian, it's kind of some concept, but you like the answer, it's right, but it is not consistent.
Okay. There was a question. Yeah.
So definitely, but we should understand, they would be cautious, use a strongly coupled set, but if you want to use a charge. I could charge out, it would be, if you know, the one charge. Leave that strongly.
Well, the particle can already be pretty heavy, right? I mean, so you can imagine there's a particle, PSM particle with a mass of 10 TeV.
But then you could get it if it's going to become set. Magnetic coupling is without.
But what would you say about dot monopoles? Do they require some couplings? Good. That's a good question. I'm not sure. That's a good question. My inclination is to say that the thing that should be hard to do is to describe particles with both electric and magnetic charge if they are very light. But I guess, no, sorry, I take it back. If they're even if they're heavy, if they have both charges, it's hard.
Yeah.
Sorry. So then, yeah, it might be part of some strong couples. You're right. Thank you.
Yes. Okay, can we thank Aleksey again? Thank you.